Hello, everyone. I'm Sean Buckley, Editor-in-Chief of Lightwave and BTR. It's my pleasure to welcome you to today's webcast, where we'll discuss the pluggable transceiver revolution. The value of pluggable optics and open line systems is becoming more apparent. This webinar describes this trend and explores how such modules can be best deployed. Today's webinar is brought to you by Nokia. To discuss these factors and how to strategize around them, it will be my pleasure to moderate a presentation from three industry experts, starting with an analyst, Michael Frankel, an analyst at LightCounting, Victor Moreno, Associate Director in Network Planning at Verizon, and following him it will be Fady Masoud, Senior Director of Solutions Marketing for Nokia. But before I hand off things to our speakers, let me quickly review our webcast setup for those of you who may be joining us for the first time or for the first time in a long time. I'll start with the Ask a Question box you should see near the slide area. I invite you to feel free to use this to ask questions at any time during the event today. To submit a question, just click in that box, type in your question, and hit the send button. We will address your questions after everyone has finished their presentations. Now, in the event you run into a technical problem during the presentation, you can call for help via the Q&A tool. Just describe your problem, hit the question submission button, and Milan, who is today's webcast technician, will be happy to help you out. Next, if you know of someone else who might benefit from seeing this webcast or you just want to revisit the presentation yourself, the event will be available on demand from our webcast archive for the next several months. We'll send you an email with the link to the archive sometime in the next day or so that you should feel free to forward to your coworkers or watch again. And the archive version, again, of the webcast will be accessible from the webcast archive section of our website, which you can reach via our homepage at www.lightwaveonline.com. If you'd like, you'll also be able to download a copy of today's slides via the Event Resources tab you should see on your screens right below the Ask a Question box. Just click the tab to reveal the slide files. And with that, let's begin our look at the pluggable transceiver revolution. Mike, the floor is yours.
Thank you very much, Sean. So my name is Mike Frankel from LightCounting. In the next 5 slides, I'm going to set the stage for the following discussions by looking at how the pluggable and in general coherent optical transceiver market has evolved over the last few years and what we might anticipate for the next several years. So pluggables have indeed been all the rage for the last couple of years at least. This slide presents a nice view of both coherent on-board modules that are not pluggable, as well as coherent pluggables and the relationship between them. And what we see here in terms of unit volume shift is that coherent on-board modules, which are the blue vertical bars, have been essentially flat in terms of units for the last 7 years. Now, what's not really apparent underneath that, of course, is that the bandwidth grew, which is not shown on this slide, by transitioning the unit in different increasing data rates. But what we also see is that indeed pluggables have seen substantial growth in volume, albeit from an admittedly low base in 2017, 2018. There's been a little bit of a pause over the last couple of years in 22 and 23, but a substantial jump in 2025 and a lot of expect very substantial growth in terms of pluggables and an increasing growth in terms of coherent onboard modules as well that are both essentially driven by the increasing relevance and the data demands of AI workloads. So diving a little bit deeper into the pluggable market, here we show a breakdown by individual module types. And what we're seeing is that over the last few years, both 400ZR and ZR Plus modules have seen roughly equivalent growth rates. However, we do expect that ZR Plus modules will see substantially higher growth in 2025, 26, and 27. After that, we see that compared to the ZR modules. After that, we see a gradual roll-off in 400 gigabit data rates and an increase and a transition to 800 ZR Plus modules in 2025, and initial volumes of 1.6 terabit ZR plus modules very early in 2026, very, very low volumes, but substantially increasing in 2027. Now, one might ask why we don't kind of see a similar transition from 800 gigabits to 1.6 that we anticipate from 400 to 800. And the reason for that is that we do see some customers who are effectively skipping the 800 gig module introduction, and they prefer to wait and transition directly from 400 gigabit to 1.6 terabits. The little kind of red line with smaller volumes at the bottom is the CFP2 modules that are mostly aligned with the Open ROADM specification. We've seen very, very low volumes shipping into that space over the last couple of years, but we do expect somewhat of a pickup going forward. Now, as we dig into the top consumers of these modules, and more specifically the top 5 US cloud companies, we do see that Amazon, Microsoft, and Alphabet kind of take the lion's share of those pluggables. Meta is not too far behind, and I believe this is kind of the first year that we're actually seeing Oracle on this chart with about 4% of the total spend. And the orange slice is kind of like everybody else. What we also see, and that is shown on the right, is that while so far top 5 companies have really seen substantial increases in the market share of kind of consuming these types of pluggable modules, going forward, we still see that they will consume a substantial fraction, but a somewhat decreasing, gradually decreasing share of the overall market. We do expect both enterprise and telecom service providers to start adopting these types of modules in increasing volumes going forward. This slide gives a slightly different view of very similar data, a little bit more of a breakdown between cloud companies in blue, telecom companies in green, and enterprise customers in red. What we see is so far enterprise customers have done really very little adoption of pluggables, but they do start to increase their consumption going forward in kind of 2025, 2026. You're actually beginning to see a little bit of that red at the bottom. And even telecom customers are beginning to consume pluggables in increasing numbers, although fractionally speaking, of course, cloud companies still consume more than 50% of that market compared to the telecom and enterprise, even going forward for the foreseeable future. So one thing that I believe differentiates LightCounting from other market analyst firms is that we actually like to compare the predictions that we've made over the years to what actually has transpired, and to double check and see whether we're on the mark, where potential deviations might be, and how we might improve our models. So the green line shows a prediction for the shipments of 400 ZR plus modules that we made in 2019. And of course, 2019, the blue line, which is the actual, overlaps the prediction. Going forward, we see that in terms of volumes, and that's on the left chart, the deviations have actually not been very significant. The predictions have worked out quite well up until 2023. In 2024, we did see that the actuals made a substantial jump. Of course, we can sort of qualify that by saying that sitting back in 2019, there was really no way for us to kind of anticipate the huge transition and the huge volumes that would start being driven by the AI revolution. But overall, in terms of volumes, the predictions have tracked quite well. The pricing on the right actually shows a little bit of a larger deviation. The reason for that is that the prices for these 400 ZR Plus modules have actually held up better or higher than the declines that we anticipated. So there's a little bit more of a deviation between the actuals versus predicted sales in terms of millions of dollars. If you would like more information, there's just I'm going to flash the slide up for all the research analysts and client services for LightCounting. And with that, I thank you.
All right, thank you very much. My name is Victor Moreno. I'm in the network planning office responsible for Verizon's transport network. Over the next few slides, I plan to share Verizon's view of the technology evolution and optics, particularly when we talk about pluggables versus our embedded base optics. Going on to our first chart, wanted to highlight some points with regards to both of the form factors that we see and that we're aware of, right? We have the embedded optics on the vertical green axis and the pluggable on the blue one. When we talk about the embedded optics, these are usually our higher performing optics, allowing us to get our longer span reaches. And this is usually due because vendors usually put in proprietary coding into the plug itself, which allows us to get to these reaches. However, these plugs do tend to be a little bit more costly, and they also have a higher power consumption threshold when we compare it to the pluggables themselves. When we look at the pluggables, these are, admittedly, they are not as, they don't have the same performance spec as the embedded cousins do, but they do come at a lower cost, and this is due to the the limited space and power design specifications with which they are designed to. More importantly, though, however, with these optics and pluggables, is that they are open, which allows us to have a better interop between the two, between our vendors and between themselves. Verizon has seen a use case for both of these, and we've done various trials when we go into the network itself. Over the past couple of years, we've had various press releases where we've partnered with our vendors, and we've used pre-production pluggables to go over our live metro network. For example, in New York City, in Long Island, and in Boston, we were able to achieve throughputs of up to upwards of 1 terabit on a wavelength over this live network. When we switched over to the embedded base, embedded optic, we were able to do in 2020 over our ultra long haul network various trials with the optics where we varied the speed, the throughput from 400 to 600 to 800 gig over various reaches, thus showing that there is a place for both an embedded optic and a pluggable variant in the network. However, this leads to the question of what's next that we see. And we saw in the previous presentation talk about 800 and 1.6, and we're seeing the same thing as we talk to our vendors, the vendor community and our partners, for both the embedded pluggable, the embedded optic and the pluggable itself. So we see we're currently at 400 gig, 800 gig is on the horizon for both the embedded optic and the pluggable. 1.6 is going to come shortly thereafter on the embedded. What we're looking to see for the pluggable itself is we're waiting to see if the design specs for space, the power consumption actually will allow the 1.6 ZR and ZR Plus optics to become readily available. The second half of the chart, we see the projected distances that our vendors are working towards and that they're designing their pluggables for. We could see that at native 800 gig, both the embedded optic and the pluggable, the reaches are about the same. It's about 500 to 700 kilometers. When we derate the optics, the pluggables themselves, to like an 800 optic to run at 400 gig, for example, that
Okay, so I think our friend Victor has some technical problems. So let's go to my section and then we'll come back. So good day, everyone. My name is Fady Masoud. I am part of the Nokia Solutions marketing team focusing on coherent pluggables. And in the next 10-15 minutes, what we're going to do is we're going to talk about the expanding the role of coherent pluggables. But in order for us to understand the evolution of these coherent pluggables and how they expand their roles, let's take a look at the current market trends shaping the optical networking industry. So let's go to the next slide. Actually, there are, just one sec. So as a matter of fact, there are three major trends. So the first one is the fact that optical engines are approaching the Shannon limit, as you can see on the slide here. This graph has, basically plots all the different generations of optical engines and the additional increase in fiber capacity they bring. You can see there are major improvements were made going from direct detect, IMDD, to coherent, and then every different modulation scheme enabled a higher bit rate that led to a significant increase in fiber capacity, all the way to the 2020s kind of time frame, where we can see the 64 QAM and PCS was the driver for delivering 800 gig per wave, 1.2 terabit per wave, and so on. However, as these wavelengths get higher in bitrate, the fiber capacity started to flatten, started to reach a plateau, if you want, because spectral efficiency is becoming more and more limited. So that actually triggered the need for network operators to think about their multi-fiber strategies, such as multi-rail. Should we go for hollow core fiber? What about the automation required for the addition of new fiber? And adding a new fiber might be viable in some options, some cases might not be viable in others. If you think about the cost and the time and the labor and all that, it's $78,000 for a single kilometer of fiber, of new fiber. So it's pretty significant in terms of cost. So now let's take a look at the second trend. So the second trend is the rise of coherent pluggables. And technology advances in DSP and CMOS from 28 nanometers to 7 nanometers to 3 nanometers actually has led to significant enhancements in the optical performance from reach and capacity perspective, as you can see on the graph here in the middle. And all this while reducing power consumption and footprint. And every generation of coherent pluggables has been reducing the power consumption per bit by 50% on average. So it's pretty significant. And this actually opened the door for using these coherent pluggables in a much broader application scope. And the third trend is the shifting priorities. Different applications have different priorities. And priorities, for example, did not change for cost and operations. They've always been important. And in some cases or some applications, capacity per fiber is the number one requirement. It's the number one thing to go after, to achieve. But sometimes it's not the main priority. But what we're witnessing here is an increasing importance to reduce the space and power. Why? Because it costs a lot of money. Just to give you an order of magnitude, it costs $300 per RU per month for footprint. That's on average. And the cost of a kilowatt hour increased around between 30% to 50% over the past 5 years, depending on where you are on the planet. And this is where when network operators start looking for new ways to further decrease the space and power by using 800 gig pluggables, coherent pluggables. So what does a market-leading 800 gig coherent pluggable look like? What are the attributes that you should look for as a network operator, as a service provider, to overcome these challenges in terms of reducing the capex, the space, and power? So that brings me to the next slide. So leading optical performance is definitely one of them. Being able to close long links at the maximum bitrate, that helps drive down the cost of optical transport, which is the dollar per bit per kilometer. Being able to operate in the C band and the L band is also key because that maximizes fiber capacity. The second key attribute is multi-vendor interoperability. And one great aspect of coherent pluggables is that established ecosystem of MSAs and interop forums where all the MSA compliant pluggables have the same operational behavior, which makes it really easy for network operators and service providers to connect a coherent pluggable from vendor A to another coherent pluggable from vendor B or over an open line system and manage them the same way. Something that transponder-based optical platforms lacked of. And this is actually was mentioned by Victor before he had this technical problem. And the other thing is to add here is CMOS, right? So CMOS makes this interoperability feasible because it provides a consistent management across the different pluggables. The third attribute is the ability to deploy over existing optical infrastructure by leveraging programmability. Networks are not the same, especially in a CSP environment, right? They have a mix of old fiber and new fiber. They have long spans, short spans, cascaded ROADMs, amplifiers, Raman, and what have you. And being able to set some of these optical parameters, like launch power, modulation, baud rate, forward error correction, is what will decide if a link can be closed at a certain bitrate. And it's not always, from personal experience, it's not always the maximum value, but it's a combination of values. Just to give you an example, a couple of years ago, we broke actually an industry record using a similar pluggable with all the knobs and the programmability over a real network, real life network, and the launch power was -4 dBm. It wasn't 0 dBm, it was -4 dBm. And the last attribute is the embedded features that help operators accelerate turnup, such as remote loopback, diagnostic tools, as well as being able to protect mission critical data through encryption. And with such versatility, 800 gig coherent pluggables will definitely change how service providers deploy coherent pluggables. You've seen the graph from Mike early on. That hockey stick to further drive down the capex and the opex, expand the application scope, and that versatility enables a flexible deployment over any infrastructure in a multi-vendor environment, which is the case for all CSPs. And that actually leads me to my next slide, talking about. Let's go to the next slide here. Talking about the multiple MSAs or deployment flexibility. So multiple MSAs and interop forums are enabling the interoperability at different levels, at the same bitrate, at different bitrates, all within the same pluggable, which is really, really key because one single pluggable can interop with different standard bodies. But the first one at the top actually comes with a high importance to a lot of network operators out there and ICPs, where an 800 gig coherent pluggable running at 400 gig is connected to a 400 gig ZR, 400 gig ZR plus pluggable at the 400 gig line rate. Why this is important? Because it enables a smooth upgrade to 800 gig routers at the service provider's own business and operational pace. So they don't have to upgrade all routers at all sites and all at once. They can upgrade based on real network demand, real network needs, and this opens the door for 800 gig coherent pluggables to be deployed in hundreds of thousands of 400 gig routers out there. And there are a lot of interop activities for coherent pluggables going on. The last one actually took place a couple of months ago at OFC. And Nokia's ICE-X 800 gig was part of the management track for port configuration and the CMIS management, as well as the performance track showing interoperability over OpenPCS with another pluggable from another vendor. So now we've talked about how coherent pluggables are changing the optical landscape. Now let's talk about the vertical integration. How vertical integration helps bringing a market-leading 800 gig coherent pluggable, for example. Okay, so being a vertically integrated company like Nokia is a huge advantage. Why? Because vertical integration is key to ensure faster innovation and supply chain security. And this, believe me, brings a lot of peace of mind well, peace of mind to a lot of customers, a lot of operators there, right? It also increases the product quality by ensuring high reliability of the different building blocks and eliminating the external sources of failure. Sometimes MTBFs are not the same, for different, coming from different vendors and so on. And finally, secure manufacturing as products are built in the European Union and the United States. So this is a very, very key aspect as well. So we've talked about versatility, enabling flexible deployment. Now let's talk about today's deployment models. And Victor actually started to talk about this before the glitch, but let me summarize that for you. So today, there are two deployment models. The first one using embedded transponders, the one on the left. We've seen earlier the evolution of the bitrate per wavelength. Think about this, taking a huge amount of traffic, from routers over gray optics and carry this aggregated traffic over 800 gig waves or 1.2 terabit waves using optical transport platforms that are designed and built from the ground up to do this, to maximize fiber capacity. This is all about packing the maximum capacity over the maximum reach, which is one of the key advantages of deploying this model. And as these transponders typically go into optical platforms that are like 10 RU high, so there is room to offer multiple client ports for aggregation. There is as well, a full suite of integrated optical functions designed for traffic grooming and aggregation and hairpinning, protection, alarm correlation, control plane. So it's a fully fledged optical transport platform. Another advantage is the operational domain separation, as these transponders act as a demarcation point between the IP and the optical domain. And this comes really handy when a lawful intercept is required. SLAs must be reinforced. You need to set a clear demarcation and set clear boundaries between the customer side as well as the service provider side. It's a great model. However, this model has some disadvantages, such as high power consumption and large footprint. Now, if you look on the right-hand side of the slide, we can see the second deployment model, which is about deploying coherent pluggables directly into routers. This is what it's called IP over DWDM. And it has the advantage of low capex, low power consumption, low footprint, because there's no optical transport platform is involved, right? And we've seen this earlier, coherent pluggables benefit from a complete ecosystem of MSAs and interop forums for a seamless line-side interoperability. So this is a big plus as well. However, this model has some disadvantages when it comes to operations and management compatibility. For example, the efforts required to certify coherent pluggables in different routers from different vendors over different OSs or operating systems. Also, this model is not designed to maximize fiber capacity because there is no traffic aggregation or packing into higher bitrate wavelengths like a transponder. So fiber capacity is less. The other thing here is there is a direct one-to-one mapping between the router port speed and the pluggable speed. A 400 gig coherent router goes into a 400 gig router port. 800 gig coherent router goes into 800 gig router port. Sometimes the 800 gig coherent pluggable has to be dialed down to 600 gig or 400 gig to close a long link, right? But that's somehow kind of wastes the capacity of that particular port because it delivers 800 gig, but it's only operating at the 400 gig. So that's one of the disadvantages. And finally, there's a lack of optical capabilities because the host is not an optical platform, and whatever optical functions supported into the pluggable cannot come at par with a fully fledged transport platform. So two deployment models, there are pros and cons for each one. Okay, so now, but should be another option, a third model in the middle, that combines some of the strengths from the other two without the disadvantages and the hassles. And that's what we call thin transponder. So a thin transponder is a set of small modules or slits that are optimized for high-speed coherent pluggables. So if you look at the diagram in the middle, a thin transponder is normally equipped in a compact modular platform or an optical transport platform with 2, 3, 4 of these units in a single RU, and providing multiple client ports for gray optics to pick up the 100 gig, 200 gig, 400 gig, even 800 gig to carry traffic from these routers, and multiple high-speed line ports for coherent pluggables such as the 800 gig ZR and a ZR Plus or a multi-haul. And this solution actually benefits from the lower power, the lower capex, the small footprint, and the optical interoperability of IP over DWDM, taken from the right side, without the operational challenges I mentioned earlier, combined with multiple client-side aggregation, the operational domain separation we talked about, some of the optical capabilities of a fully fledged embedded transponder. So it combines key functionalities from the other two into a single one. And the thin transponder also enables something it's called the technology lifecycle separation, because you think about the refresh cycle for the photonic layer, right? I mean, the refresh cycle for photonic layer, it's much longer than the IP refresh cycle. The IP is much faster than the photonic layer. And you think about the different generations of coherent pluggables. So there's a different generation every 2.5 of coherent pluggables every 2.5 years plus or take. So having a thin transponder enables service providers to benefit from these high-speed coherent pluggables, the 800 gig, all the great things they bring in terms of low power consumption, compact footprint, interoperability, and what have you, without having to wait for the optical refresh cycle. However, I mean, this solution has less fiber capacity than embedded transponders. It's about 20% less and has limited client service grooming because it's very, very compact. So, go to the next slide. Okay, so I'd like to highlight Nokia's thin transponder modules that are supported on a wide variety of platforms. For example, you can see on the left-hand side, there's the S2AD 800R. It's a half a slot model that goes into the 1830 BSS platform. On the other modules, such as we have other modules like the CHM6, CHMQ6 and CHMS8, the DDTQ2 that go into a compact modular line of products such as the 1830GX and the PSIM. Again, it's all about having the options and to have the flexibility of deployment to meet the different requirements for every application. So let's go to the next slide and see these sweet spots. Okay, so for example, when fiber is scarce and need to close long haul or subsea links with the maximum capacity, embedded transponders are the model of choice, hands down. They are built from the ground up to overcome these constraints and deliver the maximum capacity at the longer distance, period. Also, when different services must be supported, like a mix of Ethernet client and OTN client, and you need, for example, to do some optical functions like grooming and aggregation, and you carry all that aggregated traffic into higher bitrate waves like 800 gig or 1.2 terabit. So embedded transponders are the model to use. Now, okay, so let's go to the next click. When a low variety of services is needed, like you have 100 giggies, 400 giggies, 800 gig client, and space and power are limited, thin transponder does a great job driving down both CapEx and OpEx. And some of these thin transponder modules also offer some traffic aggregation functions to maximize throughput and avoid bandwidth waste. I'll give you an example, something we call the virtual bandwidth, where you can take two 800 giggies and put them on 400 gig waves, or take three 800 gig E's client and put them on 4 600 gig line. And the thin transponder also used to increase the reliability of IP traffic, leveraging the optical control plane protection and restoration schemes. Let's go to the last one now. So the third model is IP over the DWDM, and this is great when space and power are really limited, and when traffic is IP and Ethernet, native IP Ethernet. As you can see, each model has its sweet spot depending on the application and the requirement and the constraints. So now, if we want to quantify, some of you might say, well, okay, so you told me it fits between the two, so can you give me some numbers? So this is actually what this slide is all about. So what we did is we wanted to quantify the savings of each model, and we put all three models together side by side and did an analysis on different aspects for a full fiber C-band over 1,000 kilometers length. And the graph will look like this. For example, the taller the bar, the better it is, as they reflect different levels of efficiencies, from the power to footprint to capex to operational efficiency, as well as fiber capacity, as you can see on the right-hand side, and the breadth of optical capabilities. So the thin transponder provides compelling savings between the embedded transponders and IP over the WDM. So now I'd like one more click. So I'd like to finish on this slide to highlight Nokia's solutions for all three deployment models with embedded transponders, market-leading coherent pluggables that go into thin transponders, go into the 1830 PSS platform, the GX, the PSIM platform, as well as IP over DWDM with Nokia's or third-party routers. Again, it's all about providing the best solution that is right for every application. With that, I'll turn it back to you, Sean, for Victor back online.
Yep. Hi. So sorry about that. Sorry for the network glitch that we had. Hopefully you guys can hear me and see me again. Fine. Okay, perfect. So before we add the network issues, we're talking about the distances. I know Fady mentioned a couple of things that I was going to mention anyways. But just to wrap up here, on this slide right here on the right hand, we see the distances between the pluggables and the embedded are rather similar. So providers themselves, network providers like Verizon, can come to the conclusion we want to use pluggables wherever possible because of their flexibility. Should we put them in transponder shelves? Should we put them directly into router ports? What is the answer to that question? And then the answer to that question is yes, to both. It depends on the use case that we're trying to accomplish. You know, if spectral utilization is something that is not of an immediate concern, we should be able to put these coherent pluggables directly onto the router, right? This typically is seen at the edge of the network. However, as you start moving towards the right, as you see in the chart, getting closer and closer to the core, the spectral utilization becomes a premium. It's something that we have to account for. And a transponder shelf plays better in this space rather than going directly onto the router. You know, as Fady mentioned, the routers themselves, if we put the plugs onto them, we have a lower cost point, we have lower space and power, but we're also adding an extra layer of complexity that we don't have versus the classical demarcation between transport and the routed network. We need to have an optical controller so that we can have SROG propagation, so we can make sure that we have this fault restoration available to us. We also make operations a little bit, day-to-day operations a little bit more of a headache, because you now have a data-centric network operations center that has to manage things that they are traditionally not managing at all in the optical space, which is usually a domain of the transport NOC. If we look at the transponder itself, Fady mentioned about the ability to connect older generations of equipment, older generation of routers and line cards, in addition to your newer line cards, your newer rates and speeds. So these are the benefits that we see if we go with the way we build our networks today, with the routed network connected to a transport network and vice versa. Verizon's goal, and the goal that we're pushing, working with our vendors, is to make sure that we can have any pluggable go into any type of host. Right now, we have hardware interoperability. That's was showed at OFC. We have all of the vendors are working together in the OIF forum and other organizations to make sure this is possible. But we need some more, right? We need to make sure that the vendors themselves for their equipment, that their software is agnostic to the pluggable itself. Will allow a ZR Plus pluggable to go into a switch, into a transponder, into a router, and allow the equipment to also change the rates of the pluggable as it becomes available to them. There was a mention of CMIS 5.3. That compliance to that spec is it's a good first step to ensure that there's a scalable, pluggable configuration management system. But we need our vendors to take it a little bit further. We need the vendor community to agree to a standard definition of app cell codes that allow different pluggables to go and be able to have the right code for the right application. From the vendor side, for the network supplier side, we need to make sure and understand what is the right mix between proprietary mode versus an open mode. Is it more important to have longer reaches and longer spans, or is it more important to have plug and play in our optics, or is it going to be a mix? And then finally, we have to make sure that we streamline our processes so that we can take advantage of all these pluggables and make sure that our day-to-day network operations folks, they see the benefits of using these types of pluggables in the network. Finally, takeaways that we wanted to present in my section here. 400 gig is something that we have day-to-day on our ultra long haul network across the country, and we're working to double that capacity as the network improves and we augment it. When we talk about pluggables themselves, 800 gig ZR, we've done trials with them in our live network. We see them that they're working, but they're not really just yet at the spec that they need to get to. So we need to work with our vendor partners to make sure that they are fine-tuning their applications and being able to improve the software to get to the specified reach that they need to design to. As you can see, and it's been mentioned, and Fady mentioned in his section, there is a use case to have both embedded optics and pluggables in the network. You need to have them both because at the end of the day, we need to make sure that as a provider, our network is stable, our network performs at peak performance matters. And then finally, when we talk about pluggables in the routers, there is a specific use case for them and a benefit for them, but space and power is at a premium. But as we get closer and closer into the network, we need to be able to keep that separation between the two because we want to make sure that operations is maintained. And with that, I hand it over to Sean.
So it's a question for Mike. Would you have any forecast for 800 gig CFP2 DCL?
800 gig. So for 400 gig, we break it up into three categories: ZR, ZR Plus, and CFP2. Mostly because there's kind of sufficient volume in all three. For 800, so far, it's all both ZR and ZR Plus. It's all aggregated into a single number. The reason for that is that, for example, for 400 gig, total annual volumes are around 400K units. For 800 gig, there's almost, as far as I know, there's really no CFP2 volume yet. It's all about 25,000 units maybe this year that have been shipped, but none in CFP2 form factor. I believe Fujitsu announced the CFP2 pluggable around OFC 2025 timeframe in the spring.